Hello and welcome back to Instructor Allison Online Tutorials. In this video, we are going to solve problem relating to modern physics. And in this problem, a beam of neutron moving with a speed of 1010 meter per second is diffracted from a crystal of salt which has an interplanar spacing of 0.282 nanometer. Take note of this unit, nanometer. All right. Compute the de Broglie's wavelength of the electrons. So the first approach to this problem is to spell out the parameters given in the equation. When we're able to drop down the parameters, then we'll look into the formula that connects all the parameters, and then we substitute the values into the formula. Then there we go, we get the answer. So let's look into the solution to this problem. So given that, from the question, a beam of neutron moving with a speed of this. So we have speed, which we can represent it with either c or v, which is a symbol for speed, and the value assigned to that is 1010 meter per second. Meter per second is the SI unit, the international standard unit of speed. Again, is diffracted from a crystal of salt which has an interplanar spacing. Interplanar spacing, we can use D as to the symbol for that interplanar spacing. We can use the symbol D and we assign this value to it, which is 0.282 nanometer. All right, like we have the value in nanometer, we are to convert it from nanometer to meters. And that means our D will be equal to, if I should take this decimal point to this position, that means I'm counting only just once to the right. So the expression will become 2.82 times, I should have gotten something of this nature, 10 to the power of minus 1. But here, nano means 10 to the power of minus 9. So if I multiply it again to this nano, which is 10 to the power of minus 9 meters, then you can have your D converted to become 2.82 times 10 to the power of, according to product law of indices, when you're multiplying the same number of base, the powers must be added. So if we are to add minus 1 and minus 9, the result to this will be minus 10. And this minus 10 meters can also be converted as 2.82 Armstrong units, because 1 Armstrong unit gives 10 to the power of minus 10. And let's leave it here at the moment and then get order of the parameters first. All right, so we are asked to compute the de Broglie's wavelength of the electrons. So when we have of electrons, electron is very important. Sometimes they may give you the de Broglie wavelength of neutron. Sometimes they will ask for the de Broglie wavelength of electrons. So you have to take note when it is electron, when it is proton, and when it is neutron, because they have different masses. So you should also know the mass of electron, also know the mass of proton, and also take note of the mass of electron. I think in this point, since we've mentioned electron, let's put down here that the mass of electron is 9.109 times 10 raised to the power of minus 31 kilogram. All right, that is the mass of electron. All right, since we are asked to compute the de Broglie's wavelength, let's check for the formula for de Broglie. De Broglie has the formula, de Broglie expression, or de Broglie wavelength which is lambda. Of course, you know that this symbol lambda is the symbol for wavelength, and this expression is equal to, we have this Planck's constant multiplied by P, which is the momentum. And again, you know that momentum has to do with the product of mass times velocity. So I can still place this expression as this Planck's constant multiplied by mass times velocity. So in a nutshell, we could have these parameters substitute into this. So lambda now, which is the wavelength, we are looking for, the de Broglie's wavelength we are supposed to look for, will be equal to this Planck's constant. Already in the expression, the Planck's constant is not given. So it is expected that you should by now know the value for Planck's constant and the unit it is measured. And that Planck's constant is given as, or you should take note that it is 6.63 approximately times 10 to the power of minus 34. You can put it as joule per second as a unit. If you don't want to put it as joule per second, because we know that 1 joule should produce kilogram meter square, so per second. So either put it as joule per second or kilogram meter square per second. So that is the value for this Planck's constant. This would divide by the mass he mentioned here is the mass of electrons, and the mass of electron is 9.109 times 10 to the power of minus 3 kilogram multiplied by the velocity, and the velocity is given here as 101 meter per second. So we have 1010 meters per second. Now, the reasons for which I am putting the unit associated with it, not that it's very necessary, but I want to show you how we can be able to place the unit of this lambda to be in meters, because all of these parameters, some of them will cancel out, and then we have the unit of the wavelength, which is the distance between two successive crests or trough when you're talking about waves. All right, so the unit for this wavelength is in meters. We have relationship between wavelength, velocity, and frequency when you're talking about waves. All right, so at this point, let's punch in the values, all these values, on our calculator and see the value of the wavelength. So the first thing we're going to do is to multiply, is to 6.63 times 10 to the power of minus 34, which is the value of the Planck's constant. This would divide by the product of 9.109 multiplied by 10 to the power of minus 31. Here should be 1 minus 31. All right, multiply by minus 31, and this will also multiply by 1010. Then we'll have to press an equal sign to get the value of our lambda. So at this point, know that this kilogram can easily cancel out with this kilogram, and these meters, there are 2 here. You can reduce these meters, and these seconds can also reduce the second. What is left here is just meters. So you can see by the time we divide this expression, we have the unit of this to be in meters. So the answer of this wavelength, which is lambda, will be equal to, here we have a 0. About 6 zeros, 1 2 3 4 5 6, and then we have 72064, so in meters. Therefore, we want to keep this answer in standard form. So we are to move these decimal points to the right to this position. Since we have 6 zeros here, 1, 2, 3, 4, 5, 6, 7. So we'll be having 7.2064 times, we have 7 zeros at the left, times 10 to the power of minus 7 meters. So this stands to be the solution to this problem. Thank you very much for subscribing to my channel, and please, if this video is well articulated, or if you understand the concept we've introduced, please make sure you like the video and also drop a comment down below in the comment section, and also please share the video and subscribe to my channel. If you've subscribed to the channel already, please stay subscribed and then turn on the notification so that by the time I upload another video on physics or modern physics, it could be on any other branches of physics, you should be able to get notification and also follow us up. Thank you very much for joining.